Assalamu alaikum everybody. Welcome to our fifth lecture in the course Design and Analysis of Algorithms. The lecture is titled Elementary Data Structures. So clearly this is more of a revision lecture because elementary data structures are what we learned in the data structures course. However, our focus here really is on the analysis aspect. When we learned these data structures in the data structure course, we didn't have the tools to analyze the methods of those data structures. But now we have. So it's going to be brief introduction to each of these, and then followed by an analysis stating what is the actual running time of the methods. So we shall start by looking at dynamic sets. This is the name that is used to refer to all these data structures generally. And then we'll look at them individually. We start by looking at stacks, then queues, linked lists, and finally rooted trees. We shall explore trees, particularly binary search trees, in more detail in the next lecture. But here we just give a brief introduction to rooted trees generally. Okay, so let's get started. Dynamic sets. We examine the representation of dynamic sets in this lecture. And these are simple data structures that grow and shrink at runtime. This is why they are called dynamic sets. They grow and shrink at runtime. We shall concentrate on the following data structures as examples of dynamic sets. Namely, as I said in the outline there, we shall look at stacks, queues, linked lists, and then rooted trees. And as I emphasized there, we shall examine not only the methods of these data structures, but also their running times. This is actually our main focus. Now here is a list of typical operations that are common to most of these dynamic sets. There is usually a search operation or method, where in this case the search will take as parameters the dynamic set S and a certain key to search in the dynamic structure. So the search method is supposed to return to us the reference, call it X, inside the dynamic set, such that X.key equal to the target key we are looking for. Or in case the key in the K is not found, it will return nil. Alright, this is normally how search work. And then we have insert. So insert will take a new element X and try to insert it somewhere in the dynamic set S. And then we have delete. So delete the element referenced by X in the dynamic set S. Also, there is an operation to find the minimum element from the dynamic set S, find the maximum element, find the successor. So here we take in reference X, and we want to find which element follows X in the data structure S or in the dynamic set S. And similarly, predecessor, which element is the one before X in the dynamic set S. These are the common operations. Now these operations can be grouped into two, basically. those operations that will modify the underlying dynamic set. So these are the ones that I show in bold above, particularly insert and delete will actually modify the dynamic set itself. Here by adding a new element, and in the case of delete, by deleting a given element. The other set of operations are called queries because they do not actually modify the dynamic set itself. Rather, they return information about the set. Okay, return an element matching this k. What is the minimum? What is the maximum? What is the successor to x? And what is the predecessor to x? These operations will not actually change the set itself. They just return an information about the set. So let's start with the stacks. Okay, stack is a dynamic set in which the element to be removed is pre-specified. We already know which element to be removed, and that is the one that is most recently inserted into the set. And as we all know, therefore, stack exhibit the feature that last in, first out, or LIFO, meaning the same thing, last in, first out. Insert operation on a stack is called push, and the delete operation is called pop. So the operations we listed earlier on a dynamic set, they are generic in terms of their names, but when you come to stack, the operation is of insert is specifically called push, and the operation of delete is called pop. And as we all know, this is basically how stack operates. We push and pop from the one side only. The other side is blocked. You cannot remove or insert from it. And that is why we get this LIFO characteristic. A simple implementation of stack is using array, as we all know. So stack can be implemented using array as the underlying data structure. In this case, the array is assumed to store the elements starting from 1 until n, and therefore it can hold at most n elements. The array S is assumed to have attribute s.top, and by the time you use the array to implement the stack, then the stack will have an attribute s.top that returns the index of the top element. Initially, of course, is 0. Because we are indexing from 1, we can use 0 to indicate empty stack. So when s.top is 0, it automatically means the stack is empty. Now, of course, an attempt to pop from an empty stack will give an error, and that error we call it the underflow error. And similarly, if s.top is going to exceed the n, which is the upper limit of our array, then the stack is set to overflows. And therefore, if you attempt to push an element when actually s.top is equal to n, that is the kind of error you're going to receive. However, in our pseudocode, we're going to ignore this overflow condition. But obviously, if we use an array, it is going to be there. Alright, so this shows an example of stack implemented and with 4 elements already pushed onto the stack. Alright, so stack S has 4 elements, and obviously the top element is 9. So if you say what is s.top, it will tell you 4. Remember, s.top returns the index, not the element itself. It returns the index of the top element. So s.top will be equal to 4. Now here is what happens after you push an element. Okay, so figure B here is showing the stack S. After the calls to push 17 into S. So 17 will come on above 9 here, on top of 9, and push 3 will have 3 go on top of 17. Okay, so 3 is the element at the top, and therefore if you say S the top, you're going to get 6, meaning the index of the top element. Similarly, if you pop, so after the call to pop on S, basically we're going to get the 3 popped out, and S the top will move back to be equal to 5. Alright, so these are the operations we already know. Let's look at how they may be implemented. So first of all, the stack empty can be implemented like this. Simply check what is S dot top. Is it 0? If it is 0, return true. Otherwise, return false. What about push? So again, easy as we saw in that diagram. To push an element X in the stack S, what we have to do is first of all update S dot top by 1, increment S dot top by 1, and then store X at the new position of S dot top. As simple as that. And finally, the pop operation. As we said, we will in the pseudocode consider the empty case, but we're going to ignore the overflow case. So here in the pop, the first thing to do is to check that the stack is not empty. If stack is empty, return underflow error. Otherwise, all you have to do is update S.top by decrementing it by 1. So S.top equal to S.top minus 1, and then return the element that you're just gonna ignore. So return S at S.top plus 1. As we know, with array we cannot really delete an element, we can only ignore it. So by moving top backward by 1, you're going to ignore the one at top plus 1, and that is the one the pop will return S.top plus 1. We have to do it this way because, as you know, return has to be the last statement. If you say return here, it will not actually update the S.top. Right, now the question is, what are the running times of these operations? Clearly, none of this involves any loop. It's just a sequence of statements, each of which is constant in terms of its cost. And when you add constants, you're going to get a constant. Alright, so that's what we are saying here. Each of these stack operations takes order 1 time, big O of 1. Okay, so this is what we didn't know at the point we learned this operations in the data structures course. So next we look at queues. A queue is a dynamic set in which the element to be removed is also pre-specified. We know exactly which element we're going to remove, and in this case it is the element that has been in the queue the longest. In other words, the queue has the property of first in, first out, otherwise known as FIFO. So again, operations of a queue, they have specific names. So instead of insert, we call it enqueue, and instead of delete operation, we call it dequeue. The FIFO property of a queue causes it to operate like a line of customers waiting to pay a cashier, let's say in a supermarket. The first guy in front will be the first one to be processed, and delete from the queue, and then the next one and the next one and so on, as shown by this diagram. Okay, so the front element is one that we always removed, and a new element coming will be put at the back of the queue. How can we implement a queue? Again, we may use an array to implement a queue. Array again starting from 1 to n. In this case, the queue, after it is implemented with an array, it is assumed to have this attribute, queue.head. So queue.head is an attribute that will tell us the index of the front element in the queue. Okay, we also have queue.tell that indexes the location at which a new arriving element will be inserted in the queue. Now you have to be careful here. Queue.tell is not saying the index of the last element in the queue. No. Queue.tell is a free location, the next free location where we can enqueue another element. We shall see a diagram in a moment to show what that means. But queue.head actually is the index of the front element. Now the queue, unlike stack, cannot take n elements. It will take n minus 1 elements. Why? Because we want a way to distinguish between when a queue is empty and when a queue is full. So to do that, we're going to waste one of the cells. Among these n cells, we will not store element in one of them, so that we will be able to differentiate when a queue is full and when one is empty. So this n minus 1 elements will be indexed as queue.head, queue.head plus 1, queue.head plus 2, and so on until queue.tell minus 1. Remember, queue.tell is not pointing to a node or an element. It's simply a free location where we can enqueue the next one. So the last actual value is at queue.tell minus 1. And we're going to assume, as we learned in the data structure, the array being used here to implement the queue is assumed to wrap around as if it is circular. Okay, and therefore we're going to assume that location number 1 immediately follows location number n. So when you reach n, you're going to cycle back to 1 like that. So this is an example. As you can see here, we have 1, 2, 3, 4, 5 elements, and queue.head is telling us the index of the front element. So queue.head is 7. But queue.tell is not returning the index of the last element. No, the next available location where we can put a new element. So queue.tell actually is 12. And in this case, because it is 12, if we add a new element, queue.tell is going to wrap around and become 1, so that the next free location is 1. Okay, so this is what you have, for example, after inserting 3 elements. 17 was inserted, then queue.tell moved to 1 at that time. Then 3 was inserted, and queue.tell moved to 2. Then 5 was inserted, and queue.tell moved to 3. So you can see the value of queue.tell is 3. This is basically how it will work. Now you can see the last possible value we're going to have is here. So we're going to leave this space empty to indicate that the queue is full. Okay, so the last possible value of queue.tell is 6 actually. So we can put an element here. At that point, queue.tell is here. So when queue.tell is just 1 behind queue.head, we say that the queue is full. I will explain this in the next slide. So first of all, let's talk about the empty. When q.head is equal to q.tail, that is when we say the queue is empty. So initially, therefore, we will have q.head equal to q.tail equal to 1. This is how it will be initialized. But this condition can happen anywhere because we know the array is being used as circular. I mean, the q.head and q.tail do not always have to be equal to 1 for the queue to be empty. It could be anywhere. For example, if q.head equal to q.tail equal to 5, then again the queue is empty. Alright, so it could be anywhere, but initially both of them will be equal to 1. So obviously attempting to run the queue, if this is the condition, will result in underflow. What about full? When do we say a queue is full? So if q.head is equal to q.tail plus 1, meaning if you add one more to q.tail, it's going to catch q.head, then we say that the queue is full. Alright, this is why we leave that empty blank to distinguish between when the queue is full and when the queue is empty. So let's see the example again. Okay, so this diagram shows what happens after we call the queue operation. Alright, so the above shows the queue after a call to the queue run the queue. It's going to return the key 15, the former head of the queue. Alright, we'll see how it is implemented in a moment. This is the implementation of the enqueue method. We want enqueue a new element onto the queue. So here we already have a location pointed by q.tail. So that's where we want to store this new element x. So you just say q at q.tail becomes x. But you shouldn't stop there, because now you need to update q.tail. And there are two cases. q.tail could be at the end of the queue, in which case the new value should be 1. Or it could be somewhere in the middle, in which case we're going to just increment it by 1. So this is exactly what this if statement is saying. If q.tail is equal to q.length, so this is another attribute that a queue has actually, I didn't mention it earlier. q.length will tell us how many elements are there. So in case q.tail equal to q.length, then the new value of q.tail is going to be 1. Wrap it round to become the first index. Otherwise, it means q.tail is somewhere in the middle. It has not yet reached the end. So in that case, all you have to do is increment it by 1. So this is the enqueue operation. What about the queue? So to the queue, the element to be dequeued is the one pointed by q.head. So just save q at q.head into a variable x, and we're going to return that x at the end. But before that, we now need to move q.head forward by 1. So again, the same situation. If q.head is at the end, if it's equal to q.length, just wrap it around and let it become 1. Otherwise, just increment it by 1. What are the running times of these methods? Again, clearly they are both of big O1, because there is no loop involved at all in this operation. It's just a sequence of statements, each of which is constant. So when we add these constants, we're going to get another constant. As we learned, when we have a constant value, we call it big O of 1. So both enqueue and dequeue operation takes constant time. Next data structure is linked list. A linked list is a data structure in which the objects are arranged in a linear order, but unlike array, in which order is determined by indices, here the order is determined by the references. So each node in the list will have a value and a reference to the next node or the previous node or both. We're going to implement actually a doubly linked list, so it's going to be both. We will have two references, one pointing to the previous node and one pointing to the next node. So linked lists, as we already know, provide a simple, flexible representation for dynamic sets. It supports all the operations that we listed earlier. You may have noticed that stack and queue, they were not supporting some of the operations. Okay, but linked list will support all of them, including the minimum, the maximum, the successor, the predecessor. All the operations we listed for dynamic sets, they are available in the case of linked list. And this is how a linked list is represented. We have a property head, which will tell us what is the first node in the list. And then each node will have three information inside: the key and then two references. One reference will point us to the next node, and the other reference will point us to the previous node. Of course, in the case of the first node, it has no previous, so previous will be nil. And similarly, the last node will have no next, so the value of next will be nil. So this is, as I just explained, that each element of doubly linked list L is an object with an attribute key and two references, next and prev. So given an element x in the list, x.next will point to its successor and x.prev will point to its predecessor. If x.prev is nil, then it means x is the first element. And similarly, if x.next is nil, it means this is the last element. An attribute L.head points to the first element, as I explained earlier. And if L.head is nil, it means the list is empty. So again, this is the structure. Let us now try to do some operations and see how the list will behave. Okay, so this diagram is showing the list, this list in A, after the call to list insert LX, where the key of X is 25. Now here you have to be careful. Unlike what we used to have in the data structure course, where we insert an element, here actually we are inserting a node. So it's a complete, X here is a complete node. So the actual value, if you are interested in the value, you have to say x.key. So assuming x.key in this case is 25. Alright, so x here is a complete node. Just add it to the list. So in this case, as you can see, the insert will by default insert the new node at the beginning, so that the node containing 9 is no longer at the beginning. It is this new node that has been inserted that is at the beginning. So L.head will point to it. We will see the method of insert shortly. Similarly for delete, so the deletion again is a complete node X. It's not an element. All we are saying is delete the node in the list whose references matches this X. So X is a reference to a node, and we want to delete the node with that reference. And that means X can be anywhere actually. It can point to any node in the list. We shall see the implementation of that again in a moment. So here, what figure C is showing is assuming we send a node referencing to this one containing 4. So deleting that will make the next of this node containing 16 to point to 1, as you can see here, and the prev of the node containing 1 to point to the node containing 16, thereby deleting this node containing 4. Okay, let's look at the methods. So the search obviously is going to involve a loop. So here k actually is a key, it's not a node. Find this k, the value k in the list if it exists. So the way to do it is first initialize x to refer to the first node. We can get the first node by saying l.head. Okay, so x point to the first node, and then now we start a loop. As long as x is not nil and x.key is not equal to our target k, simply move x to the next. So x equal to x.next. So at the end of this loop, one of two things will have happened. Either x.key equal to our k, so we have found the target, so this x is a valid node, or x is equal to nil, in which case the target was not found, so we are returning nil. Okay, as simple as that. Obviously the running time of this operation is big O of n, because it's going to traverse the list from beginning possibly until the end. You may be lucky to find it in position 1 or position 2 and so on, but we are always interested in the worst case. This is why we are giving the big O of the operation. So in the worst case, you may have to exhaust the whole list, and you may find that actually target doesn't exist. So the running time of this method or this procedure is big O of n. Okay, what about insert? So insert a node x in the list. Here maybe I need to explain, just to remind you what is happening. So let's draw a list. We have head pointing to a node, and that may point to another node. Okay, and so on. But since we're going to insert at the beginning, this is enough for us. So this next of this is here, the prev of this is here. Of course, the prev of the first node is nil. So we come in with a node referenced by x. So x is pointing to this new node with some value. We don't care what is the value here. So the question is, we want to insert this new node at the beginning of the list. So our method is saying x.next becomes l.head. Well, l.head is pointing to this first node. So if we say x.next becomes that, basically we are saying the next of this new node should go to the same location. Okay, so x.next is this variable. Let it becomes l.head. So l.head is pointing to the first node, so the result will be the next of this x node will point to the same node. طيب. Now the second statement is saying if L dot head is not nil, because of course, as we know, there are two scenarios. We could have started with a list where L dot head is nil, meaning it is empty. Okay, so if it is empty, the operation we just did above by saying x dot next equal to L dot head simply makes x dot next to be nil. Okay, so this is nil. Okay, so the second statement now is saying if L dot head is not nil, which is what will happen in this second scenario. Okay, it doesn't happen in this first scenario. So what do we do? L dot head dot prev becomes x. Okay, so where is L dot head is here, this node, and where is the prev of this node? It is here. Presently it is nil. So we are saying change it, let it not be nil, let it become x. So basically this will point to our new node. Okay, this is only necessary if the list is not empty. If it is empty, we don't do that. Okay, because of course if it is nil, then L.head.prev is going to be an error actually. The nil doesn't have any reference. Alright, so that explains statement 2 and 3. Statement number 4 says L.head becomes x in both scenarios. So L.head is no longer going to be here, it's going to go to the same location as x. Same thing here, it's no longer going to be nil, it's going to be pointing to x. Okay, and the final operation is to say x.prev becomes nil. Because this is the first element in the list, its previous should be nil. So make this to be nil and also make this to be nil. This is the idea. So this is the operation of the insert. What is the running time of this operation? Clearly it's going to be constant. There is no loop involved in this operation. So it's big O of 1. Okay, let's look at delete. Delete the node referenced by x. Alright, so again, there are 3 possible scenarios here. Let's try to draw 3 lists to show the different scenarios. The first scenario, it could be that the node we are deleting is actually at the beginning. So L.head point to a node, okay, which point to another node, and our x, the node we want to delete, is here at the beginning. Okay, remember x is not a key, it's a whole node. So suppose we have a reference to a node in the list that we wish to delete. Okay, so this scenario number 1 where x actually point to the first node in the list. A more typical case will be where x is somewhere in the middle. So we have L.head pointing to a node, which point to another node, which point to another node, and let's say which point to another, which is the last one. Okay, so of course there are previous references. So the prev of this is here, prev of this is here, and prev of this is here. So here suppose our x is somewhere in the middle, like here. Okay, this is the second scenario where the x is pointing to a node in the middle. The node to be deleted in some way, somewhere in the middle. And the last scenario is where x is pointing to the last node. So you have L dot head pointing to the first node, which point to another node, and which point to the last node, and our x is here. Okay, you can put the reverse links to make the list complete. Okay, so we're going to see that this method actually will work in any of these three situations. Let's follow it statement by statement. So the first one says, let me change the color of my pen just to make sure you follow what I'm trying to explain. So the first line here says, if x.prev is not nil, if x.prev is not nil. So basically it's saying if it is not this case, because in this case x.prev is indeed nil, as you can see here. X.prev is nil. But in both case 2 and case 3, x.prev is not nil. Okay, so if it is not nil, then set x.prev.next. x.prev.next. So this reference, we're going to change it. Change it to what? x.next. So basically we are saying this becomes here. Okay, so if x.prev is not nil, then set x.prev.next to be equal to x.next. The same thing will happen here because x.prev is not null. So x.prev.next becomes x.next. In this case, x.next is null actually. So what will happen is we're going to set this to null, to nil. I hope you follow. Okay, x.prev will be this node, .next, this variable. Set it to be x.next. Well, x.next is nil, and therefore this variable will be nil. Alright, so this is the execution of the second statement here. Let's check. What about else? So it's saying if it is nil, however, if x.prev is nil, then we are talking about this first scenario. If x.prev is nil, we are talking about this first scenario. So what do we do in that case? We need to just update the head to become x.next. This is how to delete this node. Just say l.head becomes x.next. So l.head will come here. And at that point, this node will have no reference. Well, not yet. It still have one reference. This prev is still coming to it. So it will not yet be garbage collected until we delete this one. So we'll come to that in a moment. Okay, but notice this statement is only executed in the first scenario, because here x.prev is not nil. Also here x.prev is not nil. But here x.prev is nil, and therefore move head to go to the next node. So that explains statement number 3. Now let's look at statement number 4 and 5. Okay, so it says if x.next is not nil. So clearly here x.next is not nil. Also here x.next is not nil. But here x.next is nil. So this operation we're going to do only affects scenario number 1 and scenario number 2. It doesn't affect scenario number 3. So what are we actually saying in the body of that if statement? It says x.next.prev. x.next.prev. Okay, so this variable. Also here x.next.prev. So this variable What do we want to do to it? Let it become x dot prev. Okay, so in this case, x dot prev is actually null. So you are simply saying let this variable be null or nil. So x dot next dot prev. So this variable assigned to it x dot prev. Well, x dot prev is null. So let this be null. So you can see at this point, this node now has no reference. Okay, it was having this reference left, but now it has been broken. So it is null, and therefore it will be garbage collected. So our L.head will just point to this node. Good. Let's look at the second case. So also here, x.next is not nil. So we are saying x.next.prev, which is this variable, let it become x.prev. Well, this is x.prev. So you're basically saying let this come here. So again, in that case, this node will have no reference. It had two references, this one and this one, and both of them have been cut. So it's going to be garbage collected. And we will have the appropriate reallocation of this next will come to this node, and this previous will come to this node. So in all cases, this delete method will actually delete the node referenced by x. This is the idea. What is the running time of this delete? Again, clearly there is no loop involved, and therefore it is big O of 1. Great. So that is about linked list. The last data structure we will look at is rooted trees. A rooted tree T is a data structure in which elements are ordered in a tree-like structure. It consists of nodes which hold elements and edges which show relationship between the nodes or links between the nodes. There are three types of nodes in a rooted tree. A node could be a root, it could be an internal node, or it could be a leaf node. Alright, so all this is nothing new to us. It's more like a reminder. Now, rooted trees have the following properties. 1. They are connected. There is a path from the root to any other node. So this is unlike what we saw in graphs, where some graph may be disconnected. Trees are always connected. From the root, you can always reach every other node in the tree. 2. There are no cycles. There is only one path from the root to a node. So again, this is unlike graph. Graphs may have cycles. 3. Each node except the root has a single ancestor, has a single parent, if you like. Okay? It may have more than one children, but it will have only one parent. Property number 4 is that leaves have no outgoing edges, meaning the leaves, of course, they have no children. That's why they are leaves. And finally, internal nodes, those nodes that are neither root nor leaves, they have one or more outgoing edges. They have one or more children, basically. These are the properties of a rooted tree. And this is an example. So this is the root. As you can see, it has no parent. It has only children. Leaves, on the other hand, they have only parent, but they have no children. And then the internal nodes, okay, are like B, E, F. G is not an internal node, so also H and I, these are leaves, but J is an internal node. So an internal node will have both a parent and at least one child. As we know, the levels, the nodes of a tree can be considered in terms of their levels. So this is level 1, level 2, level 3, level 4, and so on. Now, a special type of rooted tree is binary tree, where we're going to restrict the number of children to 2. So a binary tree T is a tree whose root and internal nodes have at most 2 children. Okay, this is the recursive definition of binary tree that we know from the data structure, that a binary tree is a tree that is either contains no nodes at all, meaning it is empty, or it consists of a root node and 2 subtrees, left and right, each of which is also a binary tree. So you can define a binary tree in terms of binary tree. Now, if there are binary trees, they can also be null. So you can actually have a leaf node and so on. And this is an example of a rooted tree. The only difference in this tree from what we know from data structure is that we are adding one more reference. Each node will refer not only to its children, but also it will have an additional reference pointing to its parent. Okay, so only the root will have no parent. That's why the reference for the parent in the case of root will be nil. And of course, the tree will have an attribute called root, which will give us access to the root node. So this is what we are saying here. We represent each node of a tree by an object. And as with linked list, we assume that each node contains a key attribute. The remaining attributes of interest are references to other nodes. So for a binary tree particularly, we'll have 3 such references: P, left, and right. References to the parent, the left child, and the right child, respectively. If x.p is nil, so the parent reference is nil, it implies that x is the root. If not, x has no left child, then x.left will be nil, and similarly for the right child. The root of the entire tree is pointed by the attribute t.root, as I explained before. So if t.root is nil, it means the tree is empty. So that is the general structure of binary trees. As I said, in the next lecture, we will actually look in detail about binary search tree and come up with the methods to operate on binary search trees. And at that time, we will discuss the running times. But for now, I will just talk about one interesting tree here called a tree with unbounded branches. Okay, so trees with unbounded branching. The binary tree representation can be extended to any class of trees with at most some constant number of children k. So instead of 2, we could have 3, we could have 4, 5, and so on. Okay, but the k has to be determined. So in that case, we cannot call them left child and right child. The children instead will be called child number 1, child number 2, child number 3, and so on until child number k. However, this scheme will not work when the number of children is unbounded. We have to know the value of k. Since we do not know how many attributes to allocate in advance. Okay, you have to know that the maximum is 10, so that you allocate to each node 10 variables to refer to possible children. Of course, many of them may be null. So moreover, if the number of children k is bounded by a large constant, for which most of them are empty, then there will be a waste of memory, because we have to know in advance the maximum possible children, and we will allocate memory for each one of them. If it turns out that only few of them are actually non-empty, then we are wasting a lot of memory. The question is there a way to improve on this memory wastage? And the answer is yes. Fortunately, there is a clever scheme to represent trees with arbitrary number of children, but for which the order in terms of the space is big O of n for an n not rooted tree. So there is no wastage at all. Even though the k is unbounded, it's arbitrary, it can be any value. We don't have to know it in advance. This is called the left child right sibling representation of a tree. This is the one that will actually help us to save this memory. Left child right sibling representation. And we're going to show it briefly in the next slide, just to give you an idea before I explain it. So this is the left child right sibling representation of an unbounded tree. So each node, of course, in addition to having reference to the parent, will have two references. But this time the references are not left and right. Yes, there is a left reference pointing to the left child, but the second reference is pointing to its right sibling. Okay, in the case of root, there is no right sibling, it is the only one. So the references to the right sibling will be nil. Okay, so this is the idea. Each node will have three references, reference to the parent, reference to the left child, and reference to the right sibling. So the same thing here, reference to the left child, reference to the parent, and reference to the right sibling, and so on. So this is the idea. Let me explain it as we have here. So as before, each node contains a parent pointer P, and T dot root point to the root of the tree. So there is no change in terms of the parent, and also the special attribute T dot root, which will take us to the root of the tree. However, instead of having a pointer to each of its children, a node X only has two pointers. One pointer called x.leftChild will point to the leftmost child of node X, and x.right sibling, which will point to the right sibling of X, meaning the sibling immediately to its right. If the node X has no children at all, then its x.left child is going to be nil. And if node X is the rightmost child of its parent, then its right sibling, the x.right sibling of that node is going to be nil. Let me show you both of these cases. Okay, so here, for example, this node has no child. Okay, all the leaf nodes, you will see that they have their left child as nil. All the leaf nodes. If left child is nil, the reference to the left child is nil, it means actually it is a leaf node. Okay, so this is case number one. Case number two, if the right sibling, x.right sibling is nil, it tells us this is the last child of its parent. There is no more other parent. You see here, the reference is not nil, so there is one more child. Reference is not nil, so there is one more child to this node. And similarly here, but when we come here, the right sibling is nil. So it indicates this is the last child of its parent. Alright, this is the idea. So basically this is the representation of this of tree, which can be used to represent a tree that has unbounded number of children. And it will be able to represent it economically in terms of space. And that brings us to the end of the lecture. The rest are exercises. Let's go through them quickly. All of them are from the book in chapter 10. So it says, using figure 10.1 as a model, illustrate the results of each operations in this sequence. Each operation in the sequence: push 4 to the stack, push 1 to the stack, push 5 to the stack, pop, push 8, and pop. Show the result of this operation on an initially empty stack, which is implemented using an array of size 6 from 1 to 6. So just a diagram showing the different operations. Okay, similarly for the queue here, assuming we implement a queue with an array of size 6, again using the figure similar to 10.2, show the result of these operations. Alright, the next one is saying rewrite the enqueue and the queue to detect underflow and overflow respectively. Alright, so obviously when you are enqueuing, since we are doing it with an array, there is a possibility that the queue is full. So what modification do you have to make to the enqueue operation to take care of this? And similarly for the dequeue. And the next one says implement a stack using singly linked list L. The operations push and pop should still take big O of 1 time. So instead of using array to implement stack, implement it using singly linked list, not doubly linked list, singly linked list. Alright, implement the operation of pop and push, and they should still have big O of 1 in terms of their running time. The exercise continues in this slide. Next one says implement a queue by a linked list L. So this time it's doubly linked list, the one we just saw. Implement a queue using that. Again, the operations enqueue and the queue should still be big O of 1. Write big O of n time recursive procedure that given an n node binary tree, it will print out the key of each node in the tree. So basically a procedure to traverse the tree, a binary tree, and it should be of big O n. It should also be recursive. Next, write an big O of n time non-recursive procedure that given an n node binary tree prints out the key of each node in the tree. Okay, again the same thing like the previous one, but this time we want it to be non-recursive. However, you may use a stack as an auxiliary data structure when implementing your procedure. The final question, write an big O n time procedure that prints the keys of an arbitrarily rooted tree, the one we discussed last, with endnotes, where the tree is stored using a left child right sibling representation. So this is the only thing new actually to you. This, you have already seen them in data structure, procedure to traverse a binary tree. We did it recursively, but you can also do it iteratively if you explicitly make use of stack. But this one we didn't see because we didn't learn about this unbounded representation of tree. So it will be interesting for you to actually write this procedure. Right, so this is the end of this lecture. Thank you very much.